Welcome back. I'm glad you came back. The last section, the last video was long and probably confusing. So hopefully I can make this one shorter and I can make things more clear. So let's just review the properties of eigenvalues, eigenvectors from last time and some other interesting properties. So let's just go through. Normally in a typical class, I would have the students volunteer answers for these, but with the COVID, I'm going to have to supply all your answers. A number lambda is called an eigenvalue of A if, give the definition. So you should try this on your own, see how well you do. Hopefully you came up with AX equals lambda x for some non-zero vector x. So that's the important part, non-zero. That's the definition. Characteristic equation of A, give the definition. I mentioned this last time. The characteristic equation, which we'll work with today, is the determinant of A minus lambda I equals 0. The equals 0 is really important. It's an equation. A is invertible if and only if determinant A is not equal to 0. That's from the IMT. A is invertible if and only if lambda equals 0 is not an eigenvalue. So that is number 3 up top. AX equals 0 has a non-trivial solution if and only if the determinant of the matrix A is 0. This is the IMT. The eigenspace of A corresponding to an eigenvalue lambda is the, well, what would go in the slot? Null space of A minus lambda I. That's what an eigenspace is. It's a null space. If lambda is an eigenvalue of A, then what is an eigenvalue of A cubed? So that, again, is from the properties above, lambda cubed. But the eigenvector is the same eigenvector as A has. So if lambda is an eigenvalue of A with eigenvector x, then lambda cubed is an eigenvalue of A cubed with eigenvector x. Same eigenvector. If lambda is an eigenvalue of A, then lambda is also an eigenvalue of A transpose. That is property 5 above. If lambda is an eigenvalue of A and A is invertible, then 1 over lambda is an eigenvalue of A inverse. That is property 4 above. Finally, true or false, the eigenvalues of a matrix are on the main diagonal. False. It's only true if A is triangular. Okay. So now let's make more concrete how to find an eigenvalue, how to find an eigenvector, and do an example. To find eigenvalues, solve the characteristic equation, and that's determinant A minus lambda I equals 0. That's a polynomial equation, and you'll get some lambdas. For each lambda, if you want to find an eigenvector, you're going to solve A minus lambda I times x equals 0 for x. That's a matrix equation, and you'll do that by reducing the augmented matrix. Here is why, I mentioned this last time, but I want to do it again. Here's why solving the characteristic equation up here would give you the eigenvalues. Eigenvalues are lambdas such that AX equals lambda x for some non-zero, that means non-trivial, x. Move that lambda x to the other side, factor the x out, and you need a placeholder I there. So A minus lambda I times x equals 0. We need that to have non-trivial solutions. That's true if and only if the determinant of A minus lambda I is 0, and that's by the IMT. So that's where the characteristic equation pops up. Okay, so let's do, again, concrete example of both. We're going to find the eigenvalues, and we're going to find the eigenvectors. I'm going to show you the notation that I would like. First of all, find characteristic equation in factored form and use it to find the eigenvalues. So we're going to need the matrix A minus lambda I, which I went ahead and wrote down. And for the characteristic equation, we want to solve, well, the equation is determinant of A minus lambda I equals 0. So when you start, you're going to have 0 equals, I'm putting a 0 on the left because I'm going to have to work with this, determinant, that's a straight bar, and I'm going to put in the matrix A minus lambda I. Okay, and so that's 0 equals, let's find this determinant, that's lambda squared minus 5 lambda plus 6. All right, and now we want that in factored form. So over here on the answer bar, we're going to write down this equation in factored form. So lambda minus 2, lambda minus 3 equals 0. So important. In your textbook, in your homework on My Math Lab, they're going to just have you find the characteristic polynomial. So they'll have you write down lambda squared minus 5 lambda plus 6, but you won't have equals 0. For me, you got to have the equal 0 because that's how you get the eigenvalues, 2 and 3. You set that equal to 0. Find bases without fractions for the corresponding eigenspaces. All right, so just copying down the matrix A minus lambda I because we're going to need it. And for each lambda, we're going to find a basis for the eigenspace. So I've got 2 lambdas. I'm going to start with lambda equal 2. I need to solve A minus 2I times x equals 0. So I go ahead and I reduce the matrix A minus 2I augmented with 0. If you were writing down on a test, what would I want to see? You could take that out, and you could take this out because you would have had it written above, but you would just say, okay, I'm starting with lambda equal 2, and I'm going to reduce A minus 2I augmented with 0. And you go ahead and do that, which I did, and I get x2 is t, and x1 is 1/2 t. So my solutions look like t times 1/2, 1. So my basis vector, there would be one vector in the basis, and it would be 1/2, 1. But I want no fractions. So I can take t to be any value. I just took it to be 1 naturally. We usually do. But we could take it to be 2, and that would clear the fractions. So my basis is, bases go in squiggly brackets. Let's take t equal to 2, and then we get 2, 1. When we get to differential equations, it's really nice to have a basis without fractions. And yes, we do this in differential equations. So that's exciting. Okay, now lambda equals 3. You could skip this first. If you're writing down, your solution, you can skip all that. Just write lambda equals 3. I'm going to reduce A minus 3I augmented with 0, which I went ahead and did. x2 is t. x1 is 1/3 t. So a basis without fractions, if I take t equal to 3, I get 1, 3. Bam, I'm done. Okay. Here's one for you to try. And I did not put the solution at the end, so pause the video, do it, try and do perfect notation, pretend this is a test, and then come back and see what I do. Okay, we're back. The first thing we're going to need is A minus lambda I. So let's just write that down. That's 5 minus lambda, 3, 3, 5 minus lambda. Square brackets for matrix. No other option. Well, yeah, parentheses you could use too. Okay, now we want the characteristic equation. So I'm going to need to see 0 equals, and then I'm going to need to see the determinant sign of A minus lambda I. So 5 minus lambda, 3, 3, 5 minus lambda. Okay, so 0 equals, let's see, 5 minus lambda squared minus 9. And that equals, let's see, where can I go? Down here, 0 equals, so I still have the zeros on the left, lambda squared minus 10 lambda plus 25 minus 9 is plus 16. All right, so my equation equals 0, and I want to factor it. Not too hard. I think 2 and 8 would work. Lambda minus 2, lambda minus 8. So my eigenvalues are 2 and 8. Okay, so I wrote down the minimum that I want to see on a test. Minimum, that's it. Okay, now I'm going to write down the minimum I want to see here. For lambda equals 2, find a basis without fractions for the eigenspace. So lambda equals 2. I'm going to write down which eigenvalue I'm using. And then a minus 2i augmented with 0 is the matrix. So I go up here to my a minus lambda I, and I put in lambda equals 2. And I see I get 3, 3, 3, 3. Augment with 0. And then I go ahead and reduce, which is a one-liner, 1, 1, 0, 0, 0, 0. So x2 is free. x1 is negative x2, so negative t. So I have no fractions anyway, so I'm just going to take as my basis vector negative 1, 1. And that's minimum I want to see. All right, so a little warning. When you find the determinant of matrix, you can do row operations on that matrix and just follow along like how you change the determinant. For example, if you swap 2 rows, you change the determinant by a minus. You can't play that game with eigenvalues, all right? You cannot just go ahead and reduce the matrix because that's going to jack up the eigenvalues. And to show you that concrete example, here's a matrix A, and it's row equivalent to B. You'll just have to trust me on that, or you can do it out. But these two are row equivalent. I'm going to show you they have different eigenvalues. The eigenvalues of B, since B is triangular, we can read the eigenvalues right off the main diagonal. They're 1 and 0. 1 is a repeat eigenvalue. All right, but to find the eigenvalues of A, that's going to be harder. We take A and we subtract. We want to solve determinant A minus lambda I, the characteristic equation, determinant A minus lambda I equals 0. Since A is not triangular, we can't just read the eigenvalues off of the matrix. That's why I'm doing this work. So I write down the characteristic equation. Inside the straight bars is A minus lambda I. Now, I need that determinant. I'm going to do cofactor expansion on the middle row because that has 2 zeros. So the only term I get is the middle term. Negative, I pulled the minus out, negative 5 plus lambda, and then negative 1 to the 2 plus 2, which is 4. And then my subdeterminant is these 4 outside guys. Okay, so what does that give me? That gives me negative 5 plus lambda. Negative 1 to the 4th is just 1. And then when I do this, I get lambda squared. Well, I'll go slow. I'm going to get lambda 1 minus lambda, quantity squared, minus 1. All right, so now we'll clean that up. Negative 5 plus lambda. And then this is going to give me lambda squared minus 2 lambda plus 1, but then minus 1 is just that. Okay, so that's equal to, now I'm going to factor this, negative 5 plus lambda. I can pull a lambda out, and then I'm left with a lambda minus 2. So remember there's a 0 here. The eigenvalues of A are negative 5, 0, and 2. So they're different than the eigenvalues of B, except for the fact that they both share an eigenvalue of 0, and that's because A is not invertible. Okay. Now, I'm going to have you do one. The solution is at the end, so I'm not going to go over it with you. I want you to find the characteristic equation of A. You don't have to factor it, but you're going to have to do cofactor expansion. So go ahead and do that. And to keep this video from getting too long, what I'm going to do is stop it here, and then I'll do the next part in a second video.